Okay, so today's our last topic. After this, I've taught you all of the math I'm going to teach you guys. Yay! Yes. Alright, so just a quick reminder of the plan going forward then. Today's our last topic. My hope is that I'll do a good job of covering this today, but tomorrow, if need be, we can re-talk through this last topic, because this one is one of the more challenging ones, unfortunately. It kind of sucks that it gets left for last, but the good news is you're going to get probably one question on this on your diploma. Like, I can count on it, it'll be clockwork. You're going to get one question, only one question, so we can kind of prepare for it. So. Yeah, it actually wasn't me. I don't know why they're here. It's someone else's problem.
Well, I have to run to the bathroom.
Okay, tomorrow's a work day, and then basically next week, I don't care when, but I need you to write a quiz and a test. So I was talking with Taylor earlier. It sounds like you guys are also going to have a bio test and a social test at some point.
Wednesday. Bio was on Thursday? Yeah, bio was on Wednesday. No, Rob just came in this morning and asked me, was the bio test on Tuesday or Wednesday?
So not Thursday. Well, either way, I don't care when you guys write the test, so I'll make sure I print off the quizzes and the unit tests, because I mean, you guys know the drill. Just, grab a test mark yourself whenever. So at some point during your week next week, those are your two tasks. That and finish your assignment.
It's due on the 18th.
Yeah, let's have it due by the end of the week. Okay. One more thing though, just so that you guys can actually be done everything and not waiting on me. I'm going to give you guys my answer key for marking the assignment. It's fairly straightforward. It'll either be right because you'll have the right number, or it'll be wrong because you have the wrong number. Like, really, there is literally very little work I would expect. Like, there's a few questions where I'm going to expect some work, but like, the answer is going to be 492. And if you don't have 492 because you did 7 pick 3 rather than 7 choose 3, then it's either right or wrong. Does that make sense? So that way, ideally, by the end of next week, you can have everything done. You can probably even finish a progress log. Now that I think about it, did I give you a progress log for that? Okay, I should do that then. Okay, I should do that. But then you guys should be able to walk away at Christmas and be finished everything, ideally. Okay. Okay, let's talk about this last topic. You need to bear with me on this. This is a topic which, in my opinion, does not belong in this section here. There is an overlap with permutations and combinatorics, but it is tangential at best. But it's in the curriculum. I have to teach you it, obviously. Okay? So you have to bear with me, because this is going to seem like I am going into some crazy land. Like, what the heck does this have to do with math? I promise you there's a point, okay? So bear with me. I'm going to actually start with slide 2. Have you guys ever seen the game The Price is Right, where they do Plinko? You guys ever watch that? You have?
I've never.
You've never watched The Price is Right?
No.
Okay. Okay, so I guess for Sean's sake, just a quick explanation of how this game works. On The Price is Right, they basically give you free stuff. It's like the coolest game in the world. And contestants get randomly selected to go play like games, I guess. And this is one of their classic games where a contestant, through like a different mini game beforehand, gets a chance to earn different like little tiles, I guess, little circular discs. And the more circular discs they earn, the more chances they have to win money. And the person basically walks up to the top of the stairs, and they put their little circular disc, like say right here. And then what should happen is gravity will pull the disc down, but you don't really know exactly where it's going to go, so it might go like there for a little bit, and then clink, 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 and then eventually it might end up here, and then you earn $1,000. Or it might end up here, and you earn $500, right? And I mean, everyone's hoping to earn like the 10,000. What's mean about the way they set up the game, though, you can see is the zeros are right beside it. So, like, if you don't hit the 10,000 on either side of it, you get nothing, right? So, I mean, that one person who has, like, a great day might actually get, like, 3 of their tiles in the 10,000 spot. You earn $30,000, right? Or it might end up happening that, like, your tile goes over here and just does this the whole time, and then you earn $100 instead. So, a huge variance in that.
But either way, you're going to win.
Either way, you're probably, well, unless you get 0 literally every time. That would suck. You get what I mean, though? You guys have known this game? Okay, there's actually math and probability and patterns in this game. And so if you can kind of imagine the idea of, there's like a,
There's like probably 1,000 different ways.
Would it be fair to call it a tree diagram again? Like just the different ways that it could fall down? Like if you started here, it could go there. It could go there, like just slightly different. You know what I mean? So I'd like to simplify the problem though and go back to this very first scenario here, which is basically imagine that you have to go from point A to point B. It's kind of like the Plinko question if you take the Plinko board and just kind of tilt it sideways. If you can imagine, this is like the top of the Plinko board, and this is the bottom of the Plinko board. The only rule we have is that you have to go down and to the right. You can't do this, for example. You can't go along here, and then here, and then here, and then here, and then here. You can't go back in order to get from A to B. Does that make sense? Like, that was not allowed what I just did. What I could do is I could go like this. There. I went from A to B. Does that make sense? Like, that's a logical pathway. But that's just one logical pathway. So let me just draw some other ones in. I have different colors, so I'll just draw a bunch. You could do that. You could, in theory, go all the way over, all the way down. That's a second pathway. You could go all the way this way, and all the way down. That's a third pathway. I'll just do a few more. You could go all the way over down to here. You could go over that way, down and over. You see how the green and the yellow pathways are almost identical? But they're not. So that is a different route it can take. Hopefully you guys get the concept here. You could do that, for example. So here's my question then. How many different total pathways or routes could you take to go from A to B then? Does that make sense? Counting it out is going to be ridiculous, right? Like, I've already used, what, 5 colors? And I don't even think I'm scratching the surface as to how many there's going to be, right? Like, one of the problems with doing a diagram like this is that if you wanted to actually diagram all the different possible ways, I'm sure it's possible, but you have to be very meticulous in not counting one of them twice and not accidentally missing one of the different pathways. Does that make sense? So there is maybe a smarter way of doing something, and so maybe here's what you should write down instead. Give me a second just to go through this whole thing once, and then if I lose you, then let me talk after I finish, okay? Rather than try to figure out how many ways there are to get from A to B, maybe I should just talk about how many ways are there to go from A to C if I said C was this corner right here. I know this maybe seems like a dumb question, but how many ways could you go from here to here? The answer is 1. Like, all you can do is just walk right there. Does that make sense? Because you're not allowed to go down, over, and back up again. Does that make sense? That would not be like how gravity would pull the Plinko tile down. So there is 1 way to get to C right there. Does that work? What if I put a D right here? How many ways is there to get from A to D? 1, yeah. Literally, you can just walk there. Here's the key one then. Let's say I put spot E right here. How many ways are there to get from A to E? Good. The answer is 2, and hopefully you can see why. You can go this way, or you could go this way, so therefore it's 2. Does that make sense? Okay, here's where the stuff we've been doing actually does come together. You could go A to E through C, or, really key word there, you could go A to E through D. What happens when you have an or scenario? Yeah, there's 1 way to get to C, there's 1 way to get to D. 1 plus 1 adds to get 2. Does that make sense? Let me just try some more examples here. How many ways would there to be to get to F over here then? Well, you could go from A to C right here. There's 1 way to go there. But really to go from C to F, you just have to keep going on that same path, if that makes sense. So there's not 2 ways of going. There's really just still 1 way to get to F. You just walk straight all the way over there. That makes sense? But let's say this was G right here. See how there's 1 way to get to F, but there's 2 ways to get to E? I could go through F, or I could go through E, or means add. 1 plus 2 means there should be 3 ways to get to G. And I can actually map them out if you'd like, just to kind of show you. You could go all the way over to F and down. You could go down to D and over through E. Or you could go A to C, down through E, and over to G. So there's 3 pathways. Does that make sense? Well, if we repeat that same process ad nauseum, we should be able to calculate how far it is, or how many different pathways you can get to B. So I'm just going to erase... where's Y? There it is. I'm just going to restart this process then. How many ways was there to get to this corner right here? One way. But you know what? Around the edge of a shape, I guess a square, around the edges of this square or rectangle, really there's got to be just one way to get to this corner. Does that make sense? The only way you can get to this corner here is just to go straight through there. And the same process lies along these lines right here. How many ways are there to get down to the bottom of this corner? Just one way, right? You can just go straight down. Every intersection point then is really the sum of an or scenario where you could go this way or you could go this way. So therefore, like we've already done this one right here, this is a 2 because 1 and 1 adds to give 2. 1 and 2 would add to give 3. 1 and 3 then right here should add to give 4. And 1 and 4 should add to give 5. I'm just going to count these out just to confirm that I'm doing it correctly. To get to this corner, I say there's 5 ways. Let me try to figure them out systematically. I could go down, over, that's 1. I could go over, down, over, that's 2. Over, down, over, that's 3. Over, down, over, that's 4. And all the way over and down, that's 5. Does that make sense? So just keep the pattern going. 1 and 2 gives 3. 1 and 3 adds to give 4. 3 and 3 adds to give 6. 6 and 4 gives 10. 4 and 6 also gives 10. 10 and 10 gives 20. 10 and 5 gives 15. And 20 and 15 gives 35 ways to get to pathway B. Okay, at this point here, I don't think I can diagram them all anymore, right? Like I could do it when there was only 5. 5 was reasonable. But if that leap of logic makes sense, right, then there should be 35 ways. If I really had to, I'd go, okay, all the way over and down, that's 1. Down, partway over there. That, over, down. Over there, down. I have to say, okay, well, then I could maybe have done this over to here, down, over. This over to there, down, over. There, over. You know what I mean? Like, if I counted them all out and I made sure I didn't miss anything, then hopefully it's 35. Does that work?
The ones on the bottom. Wait, the ones on the bottom?
These ones down here?
Yeah, so you're not like multiplying anything by each other.
We're not multiplying, we're adding. There's 3 ways to go here, and there's 1 way to go here. So therefore, to go to this location here, there's 3 ways to go through this location. Or you could take the 1 way through this location. So 3 plus 1 equals 4. 6 plus 4 equals 10. Maybe here's another way of thinking about the top little section here. To get to this location right here, you could come from this direction, or you could have come from this direction. Well, there's 1 way to come from this direction, and there are 0 ways to come from the top direction because you could never have been in the top direction. So 1 plus 0 remains 1. Does that logic make sense? Well, basically it allows you to solve what's called a pathway problem then, where you're trying to figure out all of the different possibilities as to how the Plinko chip could go down the board. And hopefully you can kind of envision on a large scale, this is really a probability puzzle, right? Where I'm guessing, I don't actually know how to calculate the math, but I'm guessing that the odds of the ship landing in the 1000 square are actually less than they are in landing in the other squares. Does that make sense? Like just based on the total number of pathways for it to go, it's probably more likely that it'll end up over here than it will that it ends up back over here, just based on the pure number of pathways. Does that make sense? So, let's try a few more here. Just see to get the concept. So usually I just like to start with a basic rectangle because it's simple to start with. Basic principle is that if you want to go from A to B, everything along the edge has to be a 1. Because really, there's only 1 way to go along an edge. You just walk along an edge, right? But as you start having these intersection points, it's an or scenario where you could have gone this way, or you could have gone this way. So 1 plus 1 adds to 2. 1 plus 2 adds to 3. 1 plus 3 adds to 4, to 5, to 6. Over here, 1 plus 2 adds to 3. 1 plus 3 adds to 4. It's kind of a pattern, actually. We're going to talk about the pattern in a bit. 3 and 3 adds to 6. 6 and 4 adds to 10. 6 and 4 here also adds to 10. You guys able to follow this? Am I going too fast? I got 56. Okay, let's do the one below, if you're okay with the rectangle. Because this one below here, you can see obviously there's a bit of a challenge, right? Where this is like the Plinko problem, only they've kind of like cut out a little section of the board, and that changes things, right? What you have right here is like almost like a choke point. You guys ever heard that word before? You know what, or maybe you can kind of guess what a choke point would refer to. It's like all of the traffic needs to bottleneck through this location. If you were looking for like a real life field of study that would be similar to this, if you were like say a city manager who had to design traffic flow throughout a city, this would be a very poorly designed city because there's only one way to go from over here to over here. In Lethbridge, I have to deal with this. The choke point right here, do you guys know what this would be in Lethbridge? Yeah, Lookup Bridge. Does that make sense? Where here's the west side, here's the south side, and this is a choke point. And I had this happen a couple of weeks ago. Maybe you guys heard about there was an accident on Whoop-Up. And if Whoop-Up gets shut down, then there was like absolute chaos in Lethbridge for a little while. Because there's only a few ways on the west side, right? There's the Whoop-Up Bridge. Technically, there's also some ways to go through the highway, but then people were being idiots and there were collisions in both directions on Highway 3. And so like literally Lethbridge was at a standstill because all of the main choke points were shut down. Does that make sense?
No one was going like far down the highway, up and around like the.
You in theory could do that, I guess. Still, yeah. Like there is still that possibility as
So
well.
no one's doing it. There was a bottleneck.
Well, I mean, at some point you're stuck too, right? Like, you know, once you're stuck in traffic, can you really get back to Coaldale, go up, over, down through Picture View? Like, it's doable, but
It was nuts.
no, it was crazy.
I remember that was the week when we did zones.
Hmm.
And it happened.
Were you there?
Yeah,
Oh.
we were going towards the college though, right?
Okay.
So it was like from the bridge on with the west side, like on this side of Lethbridge.
Yeah.
All the way till like the second mall on Scenic.
Yeah.
Standstill traffic.
Mm-hmm. Yeah. That particular day, we had just finished getting groceries. We were coming back from the south side, and like we were just ahead, like behind the accident on the Whoop-Up, and so we could like see the traffic backing up. So it's like, oh, before we get stuck, we should turn off here. And then we try to find another way to get through to Whoop-Up. No, it's busy there, and like we just kept like trying to find a path. We kept having to backtrack and find a new path, and eventually we just had to give up. Like it just wasn't gonna work. Anyways, I got off topic here. Do you guys see the correlation though to like a real world problem? Okay, so let's try this one here then. There's one way to get around the periphery, around the edges. There'd be 2 ways to get to here, 3 ways to get to here, and 3 ways to get to here. And most people are okay up to that point. Here's where the issue becomes. Now we're at the bottleneck, and 3 plus 3 adds to give 6. Does that work so far? So there's 6 ways to get to the bottleneck. At this point, though, now you need to pass through that choke point. Any idea what you should put along the periphery right here? 6 is the whole way, yeah. Because if there's 6 ways to get here, there's still 6 ways to get to all of these locations, because it's just the exact same as the, you know what I mean? Like the ones. And it means there's 6 ways to get around this location. So basically at this point, then we're at the same point where you could go this way, you could go this way, so add them. So 6 and 6 is 12, and 18, 24, and 30. 18, 24, 36, 60, 90, 60, 120, 210.
I messed up.
Did anybody else get 210?
Yeah.
Okay. Not just by looking at what I did, but doing it yourself. So I didn't make a mistake. Does that concept at least make sense though as to how to go about solving a problem like this? Okay. Well, you can imagine then that, I mean, a problem like this, we can draw this out by hand, but we're essentially doing a tree diagram. Like we're counting out possibilities. It would be nice if there was a faster way. And sometimes there is. So this is where I can come back to like the permutations combination section. I do think this is very tangential. Like I don't think this is like a major focus of combinatorics, but there is overlap here. And here's where the overlap can come in. Let's say that you want to go from A to B in this rectangle right here. Rather than draw out the pathways, maybe let's write it out using some letters. So this makes sense. I could go right. Then I could go like here. I could go right, 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 and right. And then I can go down, 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 down. Does that make sense? Like that's one of the pathways I take. But let me show you another pathway and just how that would look. Let's do it in purple here. I'll just kind of do a random pathway through like the middle. According to the purple pathway, I did down, right, 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 down, right, down, right, down, and right. Count the R's and D's. Here I did 6 R's and 4 D's. Make sense? Now look in the purple pathway. I did 1, 2, 3, 4 D's, just like I did in the red pathway. And I did 1, 2, 3, 4, 5, 6 R's, just like I did in the red pathway. Doesn't logic kind of dictate that at some point I have to go right 6 blocks and I have to go down 6 blocks? I don't know when it's going to happen or in what order, right? But I could take the 4 blocks down and then the 6 blocks right. I could do 3 blocks right, a block down, 2 blocks right, a block down, 1 block right, and 2 blocks down. But regardless, at some point, does it not make sense that I have to do 6 blocks right and 4 blocks down? Well, now if we treat this more as like a permutation, what you really have is right, 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 right. You have 6 rights. And you have down, 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 down. How many blocks does the guy have to walk total? Yeah, because he's got to do 6 rights and 4 downs. So basically there are 10 blocks total that he has to walk. However, we have identical objects. The 4 blocks that are down, they're all the letter D. So when we have identical objects, we divide by 4 factorial. We also have 6 blocks that are right. And by virtue of them being right, they're all R's, right? So in a way, they're kind of identical. So it's 6 factorial. So if you guys have a calculator, can someone help me out? What's 10 factorial over 4 and 6 factorial?
Wait, sorry, where are the 6 D's?
There's 6 R's,
Oh.
and there's 4 D's.
It's 210.
210. Okay, let's go up and solve this question here. Doing the first method I showed you. Really, I should have done that first, I guess. A little anticlimactic. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. 2, 3, 4, 5, 6, 7. The first row, by the way, you can just go up by ones. If you guys didn't pick up on that pattern. It's the inner rows after that that are a little more challenging. You gotta make sure you don't mess up your math. So that'll be a 6, a 10, a 15, a 21, and a 28. It'll be a 10, a 20, a 35, a 56. Shoot, this one sucks. Carry the 1, 84? 15, woo, slow down, Chris. 15, 35, 70, 126, 210. Does that make sense? So there's a faster way. Right? And it involves, like I said, I think it's a very tangential use of combinatorics, but you can see how, here's a way that we could solve a very practical problem using combinatorics. I call it pathway problem. There is one problem with that method here. It only really works on a rectangle type shape. That same process does actually not work on a section like this. You know, can you see how like there's been like a little cut out of the section right here? That same process actually won't work, unfortunately, on this section right here, based on the fact that you're missing these little sections. So you can use that rule of basically find out how many across and how many down there are, add up how many total blocks you need to go, and then divide by like how many rights and how many downs there are. But well, let's not do this. This will save some time here, but that won't work on a shape like this, by the way. You do have to do it by hand still.
How would we do that one? Because it has the...
Oh, okay, so let's do this one by hand at the very least then. So doing this one by hand would be something like this. 1, 1, 1, 1, 1, 1, 1, around the edges. 2, 3, 4, 3, 4, 6, 10, 10. That's probably where most people get stuck. Okay, so that's the logic here is then there's still a 10 to go here. If you don't get that concept, maybe it'd be better to say that there's like a 0 right here. There are 0 ways to get this location. There's a fence preventing you from walking through here. Does that make sense? So there's 0 ways to get there. So that way this intersection point right here is the sum of a 10 and a 0. And so 0 and 10 is 10. There's like 0 ways to get to this location. So from 0 here and 10 here, there's still 10s. Does that make sense? Like basically it's 10s around the corner. So that's 20, 30, 40, 30, 40, 60, 100, 100, 200. Does that make sense? The problem with the other method is that you could say that you have to go like, say, right, 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 down, down, right, right, down, down, down. So you could say that you have to do right, 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 and you have to go down, 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 down. I guess I'm going to do this method then too.
Mrs. Fisher, can you please call 100? Mrs. Fisher, please call 100.
Does that make sense? That it looks like he has to go 10 blocks. And in those 10 blocks, 5 of them have to be right, 5 of them have to be down. And what that means then is he has to walk 10 total blocks, but there's 5 of each variety. This is not 200 because that's not the right answer. And the reason why, though, is hopefully you can kind of see, like there's this little section cut out right here. That causes issues with this method that we just did right here. Because there are some paths that aren't allowed. Like you're not able to go all the way over here and down because there's a fence preventing you from getting into this little section here. So although that method is useful, it's not always purposeful. Does that make sense? Okay. There's a pattern. And maybe some of you guys started to pick up on the pattern. I want you to imagine that you've got the same sort of problem here where you're like starting at the very, very top of the Plinko board. And it's almost like the square. I'm starting the sides of the square where you have 1 all the way down the square. There's a really smart guy named Blaise Pascal. I think it's Blaise Pascal. And he's the one who we credit with eventually kind of recognizing the pattern. And hopefully you guys can kind of see how this works. There's 1s all the way down the edges, right? This 1 and this 1 combine to give 2. This 2 and this 1 combine to give 3. That makes sense? This 1 and this 2 combine to give 3. So could you guys fill in the next couple of rows? So the next row you'd have to have a 1. 1 and 4 would put a 5 in between there. 4 and 6 would put a 10 in between there. 6 and 4 would again put a 10. 4 and 1 would give a 5, and you'd have a 1 on the edge. Let's just do one more row here. There's a 1 there. 1 and 5 gives 6. 5 and 10 gives 15. 10 and 10 gives 20. 10 and 5 gives 15. 5 and 1 gives 6, and there's just a 1 on the edge. There is a bit of a pattern to this. What do you guys notice? Say that? Good, yeah, that's what I was hoping you guys would catch. Yeah, it's symmetrical. 2 M's and symmetrical? I don't know. Whatever, you guys can figure it out. Do you guys see that concept though? Like it's a very symmetrical kind of pattern. Okay. Okay, here's where you need to bear with me. These next couple of tasks we're going to do, I promise you they're related, but boy, they're going to seem unrelated for a little while. Okay, now I want to try something completely different. It seems stupid. I promise you. Bear with me, okay? You guys remember how to FOIL things? If I gave you x plus y squared, you guys remember that x plus y squared really just means x plus y written next to itself? FOIL that. What you'd end up with is x squared. You'd end up with x times y. You'd also end up with y times x. So I'll just write it as xy a second time. You'd end up with y squared. Well, if I put that all together, the answer would be you'd have 1x squared, you'd have 2xy's, and you'd have 1y squared. You see the pattern already? Okay, don't spoil it then. Just in case someone else sees it yet. Let's say you FOIL this a third time. Okay, well, rather than writing it out as x plus y, x plus y, x plus y, what you could do is just say, let's take x plus y and FOIL that into what we just had, which is 1x squared plus 2xy plus 1y squared. See how I'm FOILing this into what I previously had FOILed out? So you got to keep track really carefully because there's a lot of terms now. X times x will give you x to the third. x times 2xy will give you 2. But now you have x squared and just a single y. Are we okay with that? Then when you go x times 1y squared, you'll have y squared with an x. Okay, so that's the first 3 things been FOILed. When I do this, I like to stack them on top of each other. So like this is how I keep track. You can do this if you like. You can use your own method. Then I'm going to times y by 1x squared. That means you're going to have 2 x's from the x squared and a y. So I'm going to write that right below this guy right here. I have 1 more with an x squared and a y. I'm just going to stack them underneath each other because they're like terms. When I FOIL this one by each other, you now have 2xy, but you have an extra y. So you have 2xy squared. Or I can write it like this. There's 2 y squareds with an x. I'm going to stack it under that one. And this one right here, I now have y to the third. Put it all together, here's what I've got. 1x to the third, 3 x squareds with a y, 3 y squareds with an x, and 1 y to the third. You guys caught up to the pattern here? Yeah. Take a look at the coefficients. 1, 2, 1. 1, 3, 3, 1. Go back a slide. 1, 2, 1. 1, 3, 3, 1. Next one we can almost predict already. So I know what the coefficients are going to be. It's going to be 1, 4, 6, 4, 1. Now hopefully we can systematically kind of figure out how this is going to work. See how here you have 3 x's and no y's? Here you have 2 x's, but therefore you have to have 1 y. Here you have 1 x, so that means you have to have 2 y's. And here you have 3 y's and no x's. What do the coefficients of each of these terms have to add together? 3. Makes sense. Because there's a 3 right here. So here if we're going to have a 4, the types of terms that you could have is you could have all 4 could be x's. Or you could have 3 x's and one of them is a y. Or it's possible that you could have 2 x's and 2 y's. Or it's possible that you could have just one of the x's and there could be 3 y's. Last possibility, you don't even have any x's and you have 4 y's. Now in terms of like the distribution, there's only one way of getting x to the 4. The only way you get an x to the 4 is you go x times x times x times x. But there's actually multiple ways of getting 3 x's with 1 y. There's actually 4 ways of doing that. And then there's 6 ways of doing this. 4 ways of doing this. 1 way of doing that. On the assignment, how many of you have done the question we have to do flip coins? You guys know the question I'm talking about? Oh, pause for breakfast first before I talk about that. Let's start with this one. Wait, how many of you have done that question about flipping coins on the assignment? No, you two have.
I started it.
Started it? Okay. There's actually a correlation with this. Let's say that you flip one coin. How many possibilities are there when you flip the coin? Yeah, I guess. You could flip and it could be heads or tails. Let's say you flip 2 coins. If you draw a tree diagram out, you could go heads gives heads or heads gives tails. And it could go tails gives heads and tails gives tails. So at the end of the day, what you really have are a possibility that goes heads with heads. There's one way of doing that. There's also the possibility that you could have heads and tails, one of each. And here is one of those where there's heads and tails. But you see how this one right here is tails with heads? It's the same thing if you don't count the order. So there's actually 2 ways of doing heads with tails. And then it's also possible for it just to be tails and tails, which is just one way of doing it. 1, 2, 1. It helps both ways. Let's just do one more row of the tree. Then this could go to heads or to tails. That's to heads or to tails. That's to heads or to tails. That's to heads or to tails. So now I'm going to count out some of the possibilities. If I go along this route of the tree, I get heads, heads, heads. There is one way of getting heads, heads, heads. It's also possible to have heads, heads, tails. Now, it doesn't have to be in that order. I just want to try to find all the routes in which you have heads twice and one tail. So, for example, heads, heads, tails, that one works. Here you could go heads, tails, heads. That still works. And way over here you could go tails, heads, heads. There's actually 3 ways of having heads twice and tails once. Okay, that's my next possibility. So then, rather than having heads 3 times or even having heads twice, now there's heads once with tails twice. And as I counted out, it looks like I can go heads, tails, tails right here. That's 1. I could go tails, heads, tails. Or you could go tails, tails, heads. That's 3. Then hopefully you can see the final possibility would be tails 3 times, which means there's no heads. And there's just the one way of doing that. 1, 3, 3, 1. That makes sense? There's the pattern. Yeah, it shows up a lot. This is one of those times where, like, when you think of how our universe and how things seem to fit together, sometimes it blows my mind that I go, wow, these things seem to be unrelated. Like, first I showed you the pathway problem. Then I showed you how to foil things. And now we're talking about the number of ways you can flip coins. 3 things that seemingly you'd think have nothing in common. And yet, mathematically, everything is in common. My preferred example for this one, actually, is based on boys and girls. Like, I think about this a lot when it comes to myself and Melissa having kids. First time I have a kid, I can have a boy or a girl. The next time we have a kid, it could be a boy or a girl and a boy or a girl. And the time after that, it could be boy or girl, boy or girl. This one's boy or girl, or this one's boy or girl. Currently, Melissa and I are on this path right here. We currently have 2 girls. Which means the next time we have a kid, I'm either having 3 girls, oh my goodness, or 2 girls and a boy. Lots of estrogen in my house. Delver, how does your family tree go?
Girl, boy, girl.
That's as far as it gets then? Okay. Okay, who's got 3 kids in their family?
I have 4.
Okay, let's use you then, since you have 4, because we can do the next row of the tree. So how does it work then?
I have 2 sisters and me and my brother.
Okay, so like it goes girl, girl to start with, then boy. And then if this were to go one further, then boy, girl. This is your route tree right here.
Yeah, pretty much.
Does that make sense? So like in Sean's family, then it goes girl, girl, boy, boy. Right? But in theory, you could get 2 boys and 2 girls by having like boy first, then a girl, then a boy, then a girl. You guys are getting what I'm saying here, right? Like there's multiple ways of getting to the point of 2 girls and 2 boys. Well, if we want to figure out how many different ways there are total, if we use Pascal's triangle, we can actually kind of systematically figure this out. In the first row, basically it's like 1 with 1. Well, then it's 1, 2, 1. Then 1, 3, 3, 1. What would the next row be? 1, 4, 6, 4, 1. In this example here, there's like one way of having 4 boys. The odds of getting 4 boys is not good. I have cousins actually. There's 5 boys in one family.
My grandma has 12 sisters.
Wow.
And yeah.
Statistically impossible, isn't it?
The last 2 were boys.
That's crazy. But like that, I mean, that is one of the routes on the tree, right? There'd be 4 ways then of having. There'd be 4 ways of having 3 boys with 1 girl. There'd be 6 ways then of having what Sean's family has, which is 2 boys and 2 girls. There'd be 4 ways of having 1 boy and 3 girls. And there's 1 way to have just 4 girls. Does that make sense how I kind of diagram that out?
Yep.
Okay.
Mine has 3 girls with 2 boys.
Okay, so I need to go 1 further down on the tree for that. Let's just write out all the ones in like of that possibility. It could go boy, boy, girl, girl. You could go boy, girl, boy, girl. You could go boy, girl, girl, boy. I'm just trying to think of all the ones that start with B. Because then I think you could do girl, girl, boy, boy. You could do
This
girl,
receiver, can you
boy,
please come
girl,
to the
boy.
office? Mr. Cleaver,
And
please
you
come
could
to the
do
office.
girl, boy, boy, girl. I think I found all 6. Does that make sense? So, then we can even get into probabilities then. Now, we don't do probabilities in this course, but if I were to ask you, what are the odds of having 4 girls? Well, so say Melissa and I have 2 more kids. What are the odds that we have 4 girls? Well, there is one way to have 4 girls out of how many total ways? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Does that make sense? There are 16 ways of having 4 kids. By the way, that 16 is really just 2 to the 4, by the way. Because it's boy or girl, boy or girl, boy or girl, boy or girl. So 2 choices 6 times. So there's 1 in 16 odds of having 4 girls. Whereas, like, say, for your family, where there's 2 of each, it's actually this one right here. There was a 6 in 16 shot of having 2 boys and 2 girls. It just so happens that your family did girl, girl, boy, boy. Right? But it could have been in a different order. Does that make sense? Okay. One more seemingly unrelated thing fitting together. I know, this is the weirdest lesson in the world. Let's skip this slide here. No, I need to explain something before we get there. Okay, find some room somewhere. I don't know why I didn't leave a room for a slide here. You know how we were making that triangle of 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. We can have that triangle there. Okay. I don't actually know who's accredited with discovering this, but there's one more link that fits together. Okay. This number right here is 0, choose 0. If you have 0 things and you choose 0 of them, there's one way to do that. Okay. In this next row right here, this is really 1, choose 0. And this one right here is 1, choose 1. Can I do 1, choose 2? That's not logical, right? Like, I can't have 1 thing and choose 2. But I can do 1 thing and choose 0 and 1 thing and choose 1. Hey, come on. Anyone want to hazard a guess as to how this row might go according to that pattern? Well, actually, you got to start with 0. Technically, you can choose nothing. You can have 2 things and choose none of them. Then you can have 2 things and you can choose 1 of them. So imagine there's 2 people and I have to choose 1 of you. Well, I've got 2 choices. And then this last one will be 2, choose 2. Now we can actually start maybe testing some of these in your calculator. This is going to be 3, choose 0. This will be 3, choose 1. This will be 3, choose 2. This will be 3, choose 3. Okay, let's actually test the next row in our calculator. This will be 4, choose 0. Let's just type it in just to confirm that I'm not just making this up. Not that I imagine you think I'm making it up, but... So, 4, math, choose 0 is 1. Do you guys know how to go like second entry just to pull up the previous example? Have I shown you that before? If your calculator can't go back up, like what you can do here is, if this is what you used to have, you know how there's like second negative gives you second answer? Don't do that one, do the one right next to it, second enter, it's entry. Oops. I screwed it up because I did it once already. I just gotta do this again. 4, choose 1 is 4. That's this one right here. Rather than have to go back and find that, I can just go second entry. It'll pull up the very last thing. And I can just go back and change out the 1 for a 2. And hey, look, 4, choose 2 is 6. Second entry, go back. 4, choose 3 is 4. And 4, choose 4 is back to being 1 again. Why can't I do 4, choose 5?
Because
You can't have 4 things and choose 5.
Yeah, that's illogical, right? Does that make sense? So one of the twists to this pyramid then is this is the row of 4s, this is the row of 3s, the row of 2s, the row of 1s, and the row of 0s. The thing about the row of 4s is that the row of 4s has 5 numbers though. Why does it have an extra number?
Because 0.
Yes, because you have to count 0. It is in theory possible to do 4 with 0 as well as 4 with 1, 2, 3, and 4. Does that make sense? So really, this is actually your 0 row, your 1 row, your 2 row, your 3 row, your 4 row. Okay. Well, this means that if I want to go do this question here now, expand x plus y to the 6, we can actually solve this without actually having to like write something out next to each other 6 times and FOIL it to death. Like that would take us forever. Using a pattern, we can figure this out. So first thing I got to figure out is how many terms will there be in row 6? And the answer is 7. Because what we have is we have 1, 2, 3, 4, 5, 6, 7. We have 6 with 0, 6 with 1, 6 with 2, 6 with 3, 6 with 4, 6 with 5, 6 with 6. Boy, I barely fit that in there. Does that make sense? But then we have to use that same logic of, remember how I was just doing boys and girls or heads and tails? Okay. There is going to be one way of having x 6 times and y 0 times. That's like, there's one way of having 6 boys. That makes sense? What's 6 choose 1? Actually, you should be able to know that in your head. It's 6, right? So that'll be 6. But now what happens is rather than it being 6 boys and no girls, now it has to be 5 boys and 1 girl. Okay, I need some help here. What's 6 choose 2? Anybody done that in their calculator yet? 15? What should come after the 15 then? That's what I'm referring to. Yeah. Now you have to have only 4 x's and 2 y's. You're ahead of me then, right? Is the next term then 20? 6 choose 3 is 20? Okay. So I need to kind of go down here. I'm running out of room here. Then you'd have 20. But how does the boy-girl combo work, or like the XY combo work then? 3 of each, right? If you guys haven't picked up on the pattern, what's happening to your x numbers is they're dropping by 1. You have 6, then 5, then 4, then 3. And what's happening to your y numbers? They're going up by 1, right? So you're going from 0 to 1 to 2 to 3. So just keep the pattern going. 6 choose 4. It is. Actually, I could have told you that without knowing using a calculator, because it's symmetrical. Does that make sense? I can actually tell you what the next number is going to be. It's going to be back to 6. All the way back to 1 again. So in terms of putting this together, now we actually have x twice and y 4 times. And then we'll have x once and y 5 times. And then for this last one here, I won't even write x because I don't need any of them. I just need y to the 6. Is it possible for me to have 6 girls if Melissa and I have that many kids? Yep, it's possible. But there's only one way for it to happen. Does that make sense? Whereas if we have 6 kids, there's actually 20 ways for you to have 3 boys and 3 girls. You can have all your boys first, all your girls. Boy, girl, boy, girl, boy, girl. Boy, girl, 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 boy, boy, right? Like, okay, you get the concept. Does that make sense? Okay, let's take a break in a second here, because now I need to kind of consolidate all this weird stuff I've shown you. Yeah, there's a formula, basically. This is the last thing I need to show you. It's this crazy formula. But why don't we take a break first? Okay. Okay, so what I've done is I've just copied and pasted the thing we just wrote out on the last slide here, at the top of here, because I want to try to explain how this formula works. This is the last formula, isn't it, on your purple data sheet there that I've given you guys, that I think we haven't covered. So other than that, everything else we've talked about in this course. So I can explain how this works. If you're looking for t refers to a term. Okay. How many terms did I write in the row here? I'd say there's 1, 2, 3, 4, 5, 6, 7 terms. Does that make sense? So we're looking, there are 7 terms. Just close the door, would you? Close the door, close the door, close the door, close the door. Thanks. Okay. Okay, let's start over again here. There are 7 terms. Did you guys You guys can follow that? There's 1, 2, 3, 4, 5, 6, 7 terms. Why were there 7 terms? Well, go ahead.
6 choose 6 plus 0.
That'll work. Maybe here's the better way of doing it. There were 7 terms because the exponent here was 6. And now to talk about what you just said, you have to account for the 0. Does that make sense? So if this exponent up here is 6, there's going to be 7 terms. Does that work? So what this notation here means is if you want to find a term, what you actually need to know first is like k is 1 less than the term you want. Okay, let's say that you want to find out, like, say this term right here. Which term would that be? Well, this would be the first term. This would be the second term. This would be the third term. This would be the fourth term. Does that make sense? Well, if this is term 4, what would k have to be then? Does that make sense? If I'm looking for term 4, it means this k is 3. Okay. Well, if this k is 3, it means that k is 3, this k is 3, and this k is 3. It does, yeah, because you see how we had a y to the third right here? This right here would tell you it's y to the third. Okay. The other number you need to know is n. And n stands for what the power of the binomial was. So you know how on the previous slide here, the power of the binomial was 6, which is why we have 7 terms, but n is now 6, which means we need a 6 right there and a 6 right there. Well, now to finish this off, 6 minus 3 right here is 3. So we have an x to the 3 and we have a y to the 3. These two things right here are going to add to be 6. And we just need to know what 6 choose 3 is, which I think you already did in your calculator. 6 choose 3 is going to be that 20. That's where this term comes from. Does that make sense? Let's try another one, just some more examples. Let's do the last term in this sequence here. So what is the last term? It should be 1y to the 6. So let's prove that. This is the 7th term, correct? Well, if we want it to be term 7, if we want to find term 7, we need this to be 6. So if that's a 6, that's a 6, that's a 6. So that explains why we have a y to the 6. We don't have any x's, though. So let's see if we can explain why we have no x's. It's supposed to be x with an n minus 6, but n is going to be 6 because it was to the power of 6, right? That still hasn't changed. That's a 6 right there. So 6 minus 6 up here means you have no x's. So you guys know that x to the 0 just means make it like a 1? We talked about that at some point. Like, we don't even need to write it, basically. We can just skip writing this whole term here. And then 6 choose 6. There is one way to do 6 choose 6. So that's where that term came from. Does that work? Okay. You guys are going to get asked one question on this. Maybe 2. But it's probably going to be 1. Okay. In perms and combs on your diploma, you get 6 questions. Okay. And I would say that you're probably going to get 1 on permutations, 1 on combinations, 1 on the fundamental counting principle. You probably get 1 with a weird twist, like Brad and Angelina have to sit together or can't sit together. You'll probably get 1 where they give you multiple identical objects of some type. And you'll probably get 1 question on this concept. So we only have to know how to do this once, but I guarantee you they're going to ask you this. So let's just do some practice questions here. I want to expand this binomial. Okay. Let's give it a try. There's a 5 up here in the corner. How many terms are there going to be? Good. I'm just going to write 6 blank squares if you don't mind. Okay, there's a 5 up in the corner. What this formula here means is first I need to start with something choose something. Well, if I'm looking for the first term, technically the first term is going to have to be 5 choose 0. Then it's going to have to be 5 choose 1. Then it's going to be 5 choose 2. Then a 5 choose 3. Then a 5 choose 4. And finally a 5 choose 5. Does that work so far? Then, in my mind, I like to think of the boys-girls kind of scenario. I could have all boys. Or in this example here, I could have 2A, 5 times. Or I could have 2a 4 times, which means that I'm going to need to have, and you got to be really careful here, but you're going to need to have negative 3b once. We should talk about that for a second. Yes. You got that. Yeah. So if there is a negative in between these things right here, you have to make the second term negative. Then for the next one, you're going to need 2a. That's like your boys, but you need 3 of them. And you need negative 3b. That's like your girls. You need 2 of them. Then the next term, now the girls outnumber the boys. I still, myself, I prefer to write in the same order consistently. So I'll still start with boys. I'll go 2a, but you only need 2 of them. And you need negative 3b, and you need them 3 times. And then here, you need 2a, you just need it once. And you need negative b 4 times. And then for the last one, you just need negative 3b 5 times. I don't even need to write the other one. I just used that formula without really even needing to use the formula. Like, let's just talk through just a given term, like say this one right here. Here's a term that is 5, choose 3. Which term is this one, though, in order? Here's the first one, the second one, the third one, the fourth one. So this is term 4. Well, according to that formula on the first slide, let's just erase some of this crap that's sitting on here. It's a bit messy. Okay, so first thing you got to do is figure out what term are you looking for. If we're looking for term 4 means that you're supposed to have a 3 right here, which means you're supposed to have a 3 right here, and here, and here. And n is based on what power the exponent was to. And in this example here, the power was 5. So that means you need a 5 here and here. Actually, that's it. So we need a 5, choose 3. Yep, we got a 5, choose 3. Makes sense? Next, wrong way. Next, we need x, whatever x was, boys. We need it 5 minus 3 times. Well, 5 minus 3 is twice. So you need whatever that is twice. Well, the whatever is 2a, and I have it twice. Makes sense? And then last step, we need the girls, in this example, 3 times. Only girls in this example is negative 3b, 3 times. Does that make sense? Let's just do term 4. Here's what you need to do then. You need to find out what 5 choose 3 is. We need to times it by 2a all squared. We have to times by minus 3b all to the third. So I need some help with someone who's got a calculator nearby. Has anybody figured out what 5 choose 3 is yet?
10.
Thank you. Then we have 2a twice. This really means 2a times 2a times negative 3b times negative 3b times negative 3b. Okay, see how I'm actually writing it out 2 times and 3 times?
So it would be 4a.
Well, actually, more so than just 4a. Like, what we need to do is take all of the coefficients and multiply all of our coefficients by each other. So I need someone to help me out here. What is 10 times 2 times 2 times negative 3 times negative 3 times negative 3? Does that make sense? All of the numbers need to get multiplied by each other. 10 times 2 times 2 times negative 3 times negative 3 times negative 3.
I got negative 1080, but I don't know if that's right.
You got that too? Okay, looks like it's right. How many a's do you have?
2. So it would be squared, then b is.
There we go. That is what our 4th term was. So we do have to simplify all of these terms here. I think I'm just going to skip to save some time here because I'm running out. But you'd have to do that for all of these terms. This term 4 is actually negative 1080 a squared b third. Let me just do one more of these terms with you, but I'll skip the rest. Let's do this term right here, term 5. So term 5 is supposed to be 5 choose 4. Then you want to have that times by 2a. Then you want to times that by negative 3b times by negative 3b times by negative 3b times by negative 3b because you're doing it 4 times. So 5 choose 4. I don't know what that is. 5? Okay. So I need someone to do 5 times 2 times negative 3, negative 3, negative 3, negative 3. Should be a positive number at least.
I got 810.
Okay.
5 times 2 times 3, 3, 3, 3, 3. Okay. But now it's positive 8, 10 because the negatives, like there's 4 negatives, so that's back to being positive. And then you could say that you have 1A and you have B 4 times. That's term 5. Okay. Again, for that analogy, these two things right here, A and B, they have to add up to 5, don't they? Right? We have 5 kids, 1 boy, 4 girls. We have 5 kids, 2 boys, 3 girls. It has to be 5. What can change though is that coefficient. You see how there's those 2's and those 3's in front there? If you have a coefficient inside the formula like this, it's going to change the coefficient up front as well. Okay, let's skip to some of the diploma questions. I think we should just go to them. So these are off of full diplomas. Like I said, you're going to get one of these. Maybe 2, probably 1. So this first one here is actually very little work you need to do. It says that when you expand this crazy thing out, there are 22 terms. What does that mean if there's 22 terms? It's not to the power of 22, it's to the power of 21. Because you always have to account for the 0. Does that make sense? In terms of how many rows, you know how we're doing that triangle, like the Pascal's cascading triangle? We're actually on row 21 in terms of how this works. Because you have to account for 0. So what that means is that your exponent equals 21. That's what this implies. What is your exponent though? Well, your exponent is 3k minus 9. Solve for k. Make sense? Okay, let's try another one. Okay, it says one of the terms in the expansion of an unknown m times x minus 4 eighth is that number. We want to find m. Okay, let's talk through what we know. It's to the power of 8. How many terms are there?
9.
You always got to make sure, like, it's always off by 1, but you got to figure out which way you're going. If you know the exponent is 8, there's 9 terms. If I tell you there's 22 terms, though, the exponent is 21. Does that make sense? So, we know that there should be 9 terms. I'm just going to write out 1, 2, 3, 4, 5, 6, 7, 8, 9. There should be 9 terms. If this is an x to the 4, which term are we talking about?
The 4th. No, the 3rd.
It's the 5th. Let's count it out.
Oh.
The first term, hopefully you'd agree, would have to be x to the 8. This is the all boys scenario. Then you could have 7 boys, 6 boys, 5 boys, 4 boys. We're looking for that term. Does that make sense? So now let's use that formula. This term right here, we're looking for term 5. The way that works is it's term k plus 1 equals n choose k x to the n minus k, y to the k. That's the formula you're given. If we're looking for term 5, what is k? Yes. Let me say that one more time just to make sure everybody catches that. Is it clear to everybody that we're being asked to look for information about term 5? Because the term 5 will be the one that has only 4 x's left. I know this is kind of weird, but we're looking for term 5, which has 4 x's. And the k value that fits into this then, if we're looking for term 5, it better be 4 is actually k. So as I start filling some of this out, it's going to be an unknown n. Actually, we do know what n is, don't we? Because n is the exponent. What was the exponent up top there? 8, I think. And then the k value, though, is going to be 4. And then we need to know what x is, 8 minus 4 times. And what y is, 4 times. Perfect. So that's a good place to start. We need 70, x to the 4s, y to the 4s. And I've been told, though, that this term right here is actually 1451520. 145
1520 x to the 4s. Does that make sense so far? Okay, x's and y's are boys and girls, heads or tails. In this example here, though, I need to be more specific. X is not actually x. X is mx. And y is not y. Y is actually minus 4. So now I just need to go make one more tweak here. I'm going to tell you that 1451520 x to the 4 is actually equal to 70 times mx to the 4. That's actually not where the bracket should go. Mx to the 4. And y in this example is not actually y. It was minus 4 to the 4. Am I okay with up to that step right there? What am I solving for? M, yeah. Yeah, now you might be frustrated or confused as to, well, okay, there's two letters though. There's M's and X's. But maybe you can see what's going to happen with the X's. There's 4 X's on the left-hand side, 4 X's on the right-hand side. They will at some point cancel. Not yet. We need to do this in the right order, but at some point they'll cancel. What I really should do is write this side out a little bit nicer. Mx to the 4 really means that it's written next to itself 4 times. So what we actually have is M written 4 times. We have X written 4 times. You also have minus 4 written 4 times. Okay. I'll just put a dot there, times by negative 256. Should it be positive? Should negative something 4 times be positive? Okay. Okay, well now that I've kind of expanded this a little bit, now is the right time for some canceling. Hey, this x to the 4, that x to the 4, ta-da, we're gone. How do I get it by itself? Well, got to get rid of 70. Sure, let's divide by 70 on both sides. I also got rid of the 256.
Oh yeah, you divide that.
You divide. I mean, what you could do is you could put 70 and 256 together. Long story short is whatever 70 times 256 is, that has to get divided by 1451520. So I need some help from that. 81? Okay. What's left on this side here? M to the 4.
So just 4 through to the other side.
Good job. And I'm feeling pretty confident that that's 3. Does that make sense?
Yep, it's 3.
That's kind of a challenging question, hey? Like, it uses the formula I've shown you, but most importantly, like, that really challenges your algebra skills. Because that's mostly what you had to do there, is you had to use the formula and do a whole bunch of algebra type work to make an equation like I did right here. But then rather than putting in x and y, I had to put in what x and y are in this context here. Kind of simplify it a little bit, cancel, and eventually solve for what m was. Yes?
Why did you divide that negative 256? Because isn't it minus 256?
No, sorry. Driana had said negative 256. It was positive 256. So that's just I just have a dot there for a time sign. It wasn't to subtract. Either way, though, everything in this, like this and this and this, they're all timesing by each other. So you definitely have to divide. You wouldn't add or subtract to get rid of any of these terms. You definitely have to divide by these terms. It was a positive 256. I knew that it couldn't be a negative 256. That's why I was questioning it, because I knew that we needed to 4th root at some point, and you can't 4th root a negative number. So.
I just did like negative 4 to the 4 and like
In the brackets. That makes sense. I know. It doesn't interpret what you're going. Well, it's very literal. It does bedmass. So it does exponents before multiply. Let's try one last one, then we'll call it a day. Okay, here's an expansion of x to the 3rd minus 4 to the 7th. So before I even get any further, how many terms will there be? Good, 8. So I'm just going to write out 8 blanks, if that's okay. I don't need to work with all 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. But there should be 8 terms. This one says, we want to know something about the term that will be x to the 12. Why will there be an x to the 12 if this only is going to the power of 7? X already has the power of 3. So if you kind of want to just kind of write out how this is going to look, what we're going to have is x to the 3 to the 7. Then you'll have x to the 3 to the 6, x to the 3 to the 5, x to the 3 to the 4. Actually, I can stop there because x to the 3 to the 4. All right. Yeah, because you multiply the exponents, right? I mean, you can keep going. I guess this would be x to the 3 to the 3, x to the 3 to the 2, x to the 3 to the 1, and we wouldn't even need x's on this last one. So, but we now at least know that this is the term we're looking for. So this is term 4. Does that make sense? So let's pull out that formula. The formula is to find a term, you need n choose k, x to the n minus k, y to the k. Okay, there were 8, no, it's to the power of 7, so there's 8 terms, but we kind of have to include 0 as a term, right? So that's where this whole little +1 business comes in. If we know that we're looking for the 4th term, hopefully you'd agree we need k to be 3 then. The reason why it's 3 is that it's actually 0, 1, 2, 0, 1, 2, 3. I have 4 fingers up now. That makes sense. So that's a 3, that's a 3, that's a 3. What's n going to be? 7, which is why we have 8 terms. So we need a 7 there and a 7 there. So let me clean this up a little bit. We need a 7 choose 3. Then we need whatever x is 4 times. What is x in this example? Well, actually x is x to the 3rd. So we need to write out x to the 3rd 4 times. And then we need whatever y is. And y is minus 4. 3 times. So help me out. What's 7 choose 3? Thank you. X to the 3 to the 4. We've kind of already determined x to the 3 to the 4 should be x to the 12, right? What is minus 4 times minus 4 times minus 4 times minus 4? What was that? Oh, sorry. Negative 4 times negative 4 times negative 4. Does that make it 64? Okay. So then, hopefully you guys would agree, we need to times by negative 64. So what we actually have is this guy right here provides the 35. This guy right here provides a negative 64. And this guy right here provides an x to the 12. I'm changing the order up because these two numbers here I have to times them by each other. So someone help me out here. 64 times by 35 with a negative. Thank you. Which apparently is A. Does that make sense? Yeah, for sure. Oh, this would be equal to term 4. And term 4 is this one right here, and we knew that term 4 is the one we're looking for because term 4 is the only one that would get us an x to the 12. Because this one would be an x to the 21, x to the 18, x to the 15, x to the 12. So first we had to figure out what term we were looking for. Then once we knew which term we were looking for, we could then use the formula. Does that make sense at all? It's very odd. Like, in my opinion, this is so tangential, if you guys know what that word means. Yeah, like, is it related to combinatorics? Yeah, I guess. But, like, barely? Like, there is stuff in common, obviously, right? Because you're using choose and the idea of adding and or being adding different ways together. Like, there are similarities, obviously, right? But it's a weird topic to throw in at the end of grade 12 curriculum. So, good news, you just got to be able to do this for one question. Does that work? Yeah, that is the downside, though, is your test is out of 40 when you're at your diploma, so each question is worth 2.5%. So if you know how to do this, you got 2.5% accounted for. If you don't know how, you got a guess at it, I guess, basically. They actually are quite cruel, and they often try to make this question numeric response. Yeah, I'll show you some examples later of how they made it a numeric response. I guess you've already seen one, like this one back here. What is numeric response? No. What they could do is rather than giving you this A, B, C, and D, they could just make you fill in the blanks, and then it would be like 2, 2, 4, 0. You are never, well, I should say never, but like the odds of you guessing and checking a question like that are remote at best, right? So, okay, I'm done. You can go if you want. You guys have any questions otherwise? Okay. Tomorrow's the work day. Sometime next week, you gotta write a couple quizzes. We're done. We're done math curriculum. Go write an essay.